I asked you to look at or read through the chapter 10, section 1 lessons. Hopefully you had a chance to do that. I'm going to talk about some of those ideas now, but I'm going to go kind of fast and a little hand wavy. I'm not going to write a ton down. I'm just going to kind of talk through some of this stuff and like do some calculator explanation and just to kind of get you up to speed on that. It's mostly definitional, so it shouldn't be too big of a deal. But you might want to have your calculator out because I'll show you a little bit of calculator stuff kind of as we go. But mostly what I'm going to do is like the examples from the notes. Just kind of walking through that stuff together, okay? So what we're doing in chapter 10 is we're introducing two different ways to conceptualize the idea of a function, which this was like the core idea in our Algebra 3-4 class, right? Our definition for a function was, a relation where for every element in the domain, you had exactly one element in the range, or for every one input, you had exactly one output. You guys remember that? Now, if you're looking at a graph of something, what was the way that you wanted to test to see if something was a function or not? Ben?
I don't know if it's the vertical test or horizontal line test. I think it's the vertical.
It is vertical, yep. So typically, in our Algebra 3-4 class, to test if something was a function, you could look at its graph and check to see if there's a possible to draw a vertical line that intersected the graph more than once, right? Now here's the question for you is, what if we wanted to create a function that where it can fail a vertical line test and still be a function? That's kind of what the impetus is behind these parametric and polar functions, is they provide you a more flexible way of defining a function so that you can create things that, for instance, fail a vertical line test, but still meet the definition of a function. So for a parametric function, what we do, coordinates in terms of x, we're going to define the x and y coordinates in terms of a third parameter that we're going to call t. So t is our parameter. So for example, if t equals 1 gives us xy is 1, 2, and if t is equal to 2 also gives us 1, 2. Well, let's say not 1, 2, let's say 3, 2. I'm sorry, that's not what I want. I want 1, 3. There we go. This would be something that would fail a vertical line test, right, if you had the points 1, 2, and 1, 3. But because we've defined our function not in terms of x's, but in terms of this parameter t, t is our input. 1 and 2 are different inputs giving us the same output, which is an xy coordinate. So this still meets the definition of a function, even though it'll fail a vertical line test when we look at the graph of it. So that's kind of the idea here, is that we want to create a more flexible system to where we can represent things that might fail a vertical line test, but we still want to be able to do, use our tools that we have available to us for functions. Is everybody okay with that notion? So that's kind of the why. Let's look at how we can graph these things on our calculator. So for example, let's say we wanted to graph x equals t squared plus 1 and y is equal to 2t for t interval -3 to 1. And again, t is called the parameter. So this set of t's that we're going to evaluate our function over is our parameter interval. So to do this, we're going to start by pressing the mode button. And the fourth line down has three options. It has func, par, pol, and seq. So it stands for function, parametric, polar, and sequential. Up until this point, you've probably never used anything other than the function mode of your calculator. But to graph a parametric, we need to change it to parametric. So move over so that the par is highlighted and press enter. Okay. Once you've done that, you can exit out of that screen. And then we'll move to the y equals menu. You'll notice in the y equals menu that this looks considerably different than it did before, right? So if there's anything in there, you're going to clear it out like I just cleared out mine. So each slash represents a new function. So every function has an x and a y part to it. So our x is going to be t squared plus 1. Just hit the variable button, the same one that you've done before, to get your t. Notice that when it was in function mode, the variable button gave you an x. In parametric mode, the variable button is going to give you a t. In polar mode, it's going to give you the theta. In sequential mode, it'll give you the n. So that's another way that your calculator is just trying to help you and remind you what mode you're in by changing the name of the variable automatically for you. Everybody good with how I typed that in? Okay. Now I'm going to go to the window here. So the first place in my window is my range for t. The parameter for my interval that's given is -3 to 1. So I'm going to change the t min to -3. And the t max to +1. The t step I'm never going to change. I'm just going to leave it whatever the heck it was on the problem. The window now in which I'm going to look at this graph, I'm just going to use kind of my standard window that I might have to graph something in function mode. So I'm just going to go -10 to +10 for both x's and y's. And whatever the x and y scales, I'll just have it 1, and the everybody okay with that? So again, the x min, x max, y min, y max is just describing how the shape of your window that you're about to look at your graph on. So same as it did before in function mode. So then I'll just hit graph, and this is what I get. I get like a piece of a parabola is what that looks like to me, right? Notice here that this fails a vertical line test, right? But we're able to generate this graph completely with one function, or like one input to our y equals menu. We're able to generate this graph that we couldn't have in function mode, right? In function mode, you couldn't have drawn this with just one input. You could have pieced it together if you were sneaky, but that's pretty cool, right? Let's do one more real quick here. So I'm going to go clear this stuff out, and I'm going to do cosine t and sine t. Okay. And we'll go back to our window. Oops, I want to do something in my mode menu here first and change that to Radian mode. My calculator is in degree mode, so I'm going to change mine to Radian here before I try to graph anything with sines and cosines in it. You know what I mean? Okay. So my interval for my parameter, what would be a reasonable interval for my parameter interval here? considering we're doing sine and cosine? Ben?
So like maybe like the unit circle should be like negative 1 to 1.
Okay, but remember t is the parameter that we're taking sine and cosine of, right? So if I wanted all possible values here for this graph, sine and cosine are periodic functions, right? Meaning that their graphs repeat after a certain interval. What is that interval called?
Wait, are you saying like the range of it? So like I remember like last semester like we were having like pi with like half pi and like pi
Okay.
for interval range.
So you're thinking of the inverse functions, I think. Yep. So what about just regular sine and cosine? How long on the x-axis does it take before the graph repeats itself? 2 pi, right? In fact, the period is 2 pi for both sine and cosine, right? So any section that's 2 pi long, we should get all the possible values for sine and all the possible values for cosine to come out. You guys agree with that? So I'm going to set my interval or the parameter interval to be 0 to 2 pi. And if you think about this then, the coordinates for whatever I'm going to graph are going to be cosine t comma sine t, right? We already know what this graph should look like. What graph has coordinates cosine theta sine theta? It's a circle, specifically the unit circle. So the window that I could use here should just go from like -1 to +1. I'm going to do -2 to +2 just so I have a little bit of buffer there for both x and y. And then let's hit graph. And there I'm getting a circle with just one function input, right? Again, if you tried to do this in function mode, you'd have to piece this together with 2 inputs at least. Vicky?
Mine says it's valid.
Okay, so you probably did like swap the +2 and the -2. Like you probably have them in the x min as the positive and x max as the negative. Or
No, that part's right.
how about the y?
That part's right. Yes.
Well, the invalid. Oh, one other place we could check. If you go to the y equals, are any of these plots highlighted? We're up at the top where it says plot 1, plot 2, plot 3. Unhighlight that and then try it again. You're welcome. Yes, sir. Yes, sir. Okay, so that's a little bit on how to use your calculator to graph these parametric functions. Everybody okay with the calculator piece? Victoria?
My vector just died. One.
Yeah. Okay. So let's do some examples from section 1 here. Okay. So let's say that we want to eliminate the parameter for this parametric function. When we say eliminate the parameter, really what we want to do is we want to rewrite this as, rather than a function in terms of t, we want to write it as a function in terms of like x, like we would normally. Everybody okay with that idea? So what I'm going to do, and I'm going to solve that in terms of t. So I'm going to subtract 2 from both sides and then divide by -3. Everybody good there? And then I'm going to plug that in for the y. So when I do that, I get x plus 1 over 3. I did some simplifying there in my head, but all you're basically doing is solving a system by substitution, right? But here's the catch. This is not quite complete. Because like we've seen before when we graph these parametric functions, the domain and range for that parametric function in terms of x might not be exactly the same because you might not get the whole graph, right? When we did that sideways facing parabola, we got like just a piece of the parabola, not the entire parabola. So we have to be a little bit careful here. We also have to specify the domain and range for this function because it might not be the implied domain and range just from looking at this function. So how are we going to do that? What we do is we go back to our original function. And what we're going to do is to figure out the domain, we're going to look at which coordinate, x or y. X, right? The domain is always about the x coordinate. And we're going to look at the range of this function where t is the domain. So what kind of function is 2 minus 3t? That's a linear function, right? If the domain for a linear function is all real numbers, what are the possible set of outputs I can have for that? Also all real numbers. Everybody agree with that? Okay. Then let's look at the y. That's going to tell us about the range. Again, to figure out y, we're going to look at the range of the function f of t equals 1 minus t, where the domain, again, is all real numbers. If I look at that function, 1 minus t, what kind of function is that? Again, linear function. If the domain for a linear function is all real numbers, what does its range have to be? All real numbers. So this one, nothing special happened. Its domain and range would be exactly its implied domain and range. Let's look at an example where that doesn't happen. Sound good to you guys? Okay. All right. So here is my parametric function. If I'm going to eliminate the parameter, the first thing I'm going to do is solve one of the variables in terms of t. I almost always am going to solve x in terms of t because it leaves less cleanup at the end if I do it that way. So t is going to equal x over negative 4. And if I plug that into the y equation, I get x squared over 8 plus 1. We okay with that? Ben?
I get t equals x over -4. Did you solve it?
I just solved the x equation in terms of t. Yeah, no problem. Okay, so let's look at the domain now. So I'm going to look at this function f of t equals -4t. And I'm going to find the range of that function where the domain is -2 to +4. What kind of function is -4? T. Linear. Okay? So a linear function basically is going to look like a line like this or a line like that. Everybody agree? So its range is either going to be f of the beginning of my interval for the domain to f of the end of my interval for my domain, or the opposite, right? Everybody agree with that? Since a linear function is constantly increasing or constantly decreasing, the endpoints of the domain are going to tell me the start and end of the range. Everybody agree with that? So that's all I'm going to do here, is I'm just going to go ahead and plug in my two values that I have for domain. So my domain is going to be -16 to 8. How did I know that it was an 8 to -16? Yeah, because we always write our interval from the smallest number to the biggest number, right? That's just the convention we use. Remember, as it's really describing a range of values. There are no values that go from +8 to -16, right? That would be empty. Everybody's good there? Okay. So now we'll do the same with the y coordinate. What kind of function is y? Quadratic. So what does the range for a quadratic function look like? Ben? Okay. We'd say the minimum to infinity, or -infinity to its minimum, right? Depending on whether our parabola is opening down or whether it opened up. Everybody agree with that? Can we look at this quadratic equation and tell whether the parabola opens up or down just by looking at it? Yes. Which one is it? Up. Because the leading coefficient is positive. Exactly. So this parabola is opening up because its leading coefficient is positive. Everybody's good with that? So we still need to find that minimum value. Where is that minimum value going to be located? What point on the parabola? Like more generally than that, we have a name for that point, right? The vertex. Everybody agree with that? How do we find the vertex for a quadratic? How about -b over 2a? And then f of -b over 2a. Do you guys remember that? Does it look familiar, though? It should at least look familiar, even if you didn't remember it. So in our case, our vertex is going to be located at 0 over 2 times 2, 0. And if I plug 0 in, I get 1. So my range begins at 1. Everybody okay with that? Now to find the other end of my vertex, or I'm sorry, the other end of my range, I'm going to use the -2 and +4. I'm going to plug those both in and see which one gives me the bigger value. So I get 9, and then I get 33. So this should go to 33. Is that okay with everybody? Again, what's a good way to confirm that you've done this correctly? To graph it on your calculator and look at the picture just to make sure, right? You don't need to do that. You shouldn't need to do that. But as you're learning how to do it, it's a nice way to kind of check your own work and get some insight as to like what's going on. Everybody cool with that? Okay. What if we wanted to do the reverse? What if we wanted to take a function in 2 variables and rewrite it as a parametric? Do you think this is going to be harder or easier? It is way easier. Because there's a cheaty way to do this. Let's look at what do we have again. The cheapest and easiest and sneakiest way to do this. What if I just replace x with t? Then y would be 3t minus 1, right? Done. Well, almost done. We still need to define our interval. But the domain here would give us our interval here, since x is just equal to t, right? So what type of function is y equals 3x minus 2? Linear. What's the domain for a linear function? All real numbers. And we're done. I think that's considerably easier, right? Okay. What if instead of giving you a linear function, if I give you 2 points? Actually, let's make this less trivial. Say the line segment between these 2 points. What's going to be the easiest way to do this? The easiest way to handle this is to use the vector equation for a line. So what does V naught stand for? What kind of vector is that? That's a point vector, right? Does it matter which point I use to create V naught? It does not. So let's just say I use the first point. So far, so good. What is the vector V representing? That's the slope vector. Everybody's okay there? Okay. So my parametric function is going to be x equals -1 plus -7t. My y component is going to be 4 plus 1t. Everybody okay with that? And here's the rad dad part. Is the tricky part about this would, if you didn't do it this way, would be have to find your interval for the parameter. But here it's quite straightforward. So if I pick 0 for t, what am I going to get? I'm going to get that point, right? Everybody agree? If I pick t to either be 1 or -1, I should get the other point. So all I need to do is check when I plug 1 or -1 in for t, which one gives me 6, 3. Should be pretty easy to see that that's going to be -1. So my interval then would be, brackets, -1 to 0. But it's always going to be either 1 or -1, which is the nice part about using the vector equation for a line, is that you know what that parameter interval is going to look like. It's always going to be a unit interval. Okay with that? All right. On to section 10.2. So one of the natural extensions to parametric equations is to motion. Because if you think about it, when we're describing motion, we want to describe the position of something. Essentially, it's xy coordinate per unit time, right? Because time is typically affecting the position of something when things are moving. Everybody okay with that? So if we do this without a parameterization, we have a position equation in terms of time. A velocity equation in terms of time. and this is for one-dimensional motion, right? Basically just things falling straight up and down. And just FYI, the units here are in feet. So the gravity that I'm using here, I'm describing in feet as well. So this is like English units. For those of you that are in physics that are used to, you know, using meters and whatnot, we're not doing that right now. And I'm just loading something so I can pull an example without having to write it all down. If it ever wants to load. Come on. Finally. Maybe. Think about it. Anytime you want to go, computer. Because it takes this long to copy and paste something, apparently. And then it just decides to put it wherever it wants also. All right. A ship stranded in the ocean. On top of the bridge, 80 feet above the water, distress flare shot straight up with an initial velocity of 72 feet per second. Provide a graph of the flare's height against time, and then find the height of the flare above water after 1, 2, 4, and 5 seconds. So this is a position function, right? Because we're talking, it's asking the position of the flare. It says the initial velocity is 72. Initial height is going to be 80 feet. Everybody's okay there? So to graph this, I'll go to my calculator and turn this back into function mode. and we'll plot this. I'm going to put x's there where the t's are because we're in function mode. The window that I'm going to set, well, x is time, right? So 0 is my start. And I have to cover at least 5 seconds, so I'm going to do a little bit more. I'm going to go to 6 because we want the position of the flare at 1, 2, 4, and 5 seconds. The y is going to be the height of the flare, so the minimum height it can have is 0, basically when it's back on the deck. Right? I don't know how high it can get. I'm going to just take a stab and say, starting at 80 feet, I don't know, 200 feet or something. Just guessing. So let's hit graph and take a look. So here's my flare. Everybody okay with that? So if I want the heights at 1, 2, 4, and 5 seconds, one easy way to do that is press second and then trace and choose the value command. That's going to put this little x equals at the bottom, and then you can pick a value for x. It'll find that value on your graph and also report the y coordinate that goes with it. So the height after 1 second is 136 feet. Ben? My mode is in function mode. I just 0 to 6 and then 0 to 200. Yep. Again, 0 to 6 is the only one you should have definitely come up with. And then the other one is just a guess, right? And you might have to guess more than once to get a decent window, but you're welcome. Are you guys good with doing that? And you could do that again for, again, pressing second, trace, choose the value command, and you say, let's do 2 this time. And you can keep doing that to get all your heights. Does that sound okay? Now, question for you guys. The graph here, does that really represent an accurate picture of what the flare is doing? Not really, right? Because this gives you the impression that the flare is going like this. What is the flare really doing? It's going like that. So we can make a better graph than this if we use a parametric function. So let's move this into parametric mode. And now let's so is the x coordinate changing in this situation? No. Right? So let's just pick a value for x that'll just be constant. I'm going to use, I don't know, 2. Doesn't really matter. You can pick any value of x you want. It's not changing, so it's just a constant, whatever. The y coordinate should be changing, and it should be changing by this motion equation that we just described. So negative 16 t squared plus 7t plus 80. And then for my window, my value for t should be 0 to 6. My value for x, 0 to 6 is fine, right? The x just needs to cover, the number 2 needs to be included, that's it, right? Other than that, it doesn't matter. And my y, we used 0 to 200 before, should be the good for my y here. So let's hit graph, and here, make sure you're watching when I do this, because it'll be a little bit intuitive or informative as to what's going on. Let's get graphed. Look at where it started, right? Started in the middle at like 80 feet, drew up, drew down, and then drew the bottom, right? That's actually describing what the flare is doing there. Is that okay with you guys? Okay. Next up is nice, but no, I can do that. I guess. Oops. So remember here, the V that I've described here is a vector V. What do the bars around a vector mean? Is that absolute value? No. What does that mean? Magnitude. So it's basically just the value for the velocity, right? For the most part, that number is just going to be given to you in your problem. And then everything else still is the same. Like the time is measured in seconds. The distances are measured in feet. We're using the English unit constant for gravity. So let's look at some examples now. Come on. Apparently copying and pasting from one document to another is like a huge task for my computer right now. Because we've been waiting a good like 30 seconds for it to copy and paste like a paragraph, maybe. Actually, it's more like 2 sentences or 3 sentences. But like, anytime you want to do that here, computer. Good Lord. Right? Like that little, I probably could have typed it in faster. All right, let's look at an example. You hit a baseball at 3 feet above the ground with an initial speed of 135 feet per second at an angle of 16 degrees above the horizontal. Will the ball clear a 15-foot fence that is 300 feet away? If yes, by how many feet? If no, how high up the wall will the ball hit? Well, first thing we should do is decide whether we should be using our position equation or our velocity equation. Which one would I want to be using in this case? Ben? Why? But what are we being asked for? Okay. That's a position question, right? So you have to look at what you're actually being asked for. So we need the position equation. So velocity is 135. The angle is 16. Then we have our t squared plus 135. And our initial height of the ball is 3, right? since that's where the height of the ball that we're hitting it from, right? Okay, so let's do this algebraically, and then we'll also do this graphically and kind of show you that the two are matching up, okay? All right. So, first thing that I'd want to do, we're trying to see if the ball is going to clear this fence, right? So basically, I know one part of my position. I know the x component of my position, right? How far does the ball need to travel horizontally? 300 feet, because that's where the fence is. So what I'm going to do is I'm going to plug 300 in for the x component. And I'm going to solve then for t. Plug that into the y component to figure out how long it takes to go 300 feet. And then at that time, how high will the ball be? Everybody good with that plan? .51 feet. Since that number is less than the 15, we know the ball didn't clear the fence. Everybody okay with that idea? All right. Let's do this with a calculator now. So again, I'm going to go and I'm going to type in my two-dimensional motion equation. Cosine times t. Oops. Got to make sure I'm in degree mode now. I switched to radian mode earlier. Let me do that real quick. Okay, now I'm ready to go back. Negative 16 t squared plus 135 sine 16 times t plus 3 and then I'd also like to draw the fence, right? That would be nice to see if we're going to look at the graph. So I'm going to go and make this the thick line. The x-coordinate for the fence is constant at 300. And to draw the fence all the way up to 15, I'm going to do 15 times t divided by t max. Everybody okay with that idea? So to get the t max to show up, I'm going to press the vars button. I'm going to go to window. I'm going to go over to t/theta for my parametric or polar coordinates. And I'm going to grab the tmax command. So what this is, it's, let's say the tmax is 6. I'm going to get, and my t's go from like 0 to 6. I'm going to have like 0 divided by t, which is just 0. So I'm going to get a height of 0. And like 1 divided by 6, or 1/6. So I'll get my next height at like 1/6. And it'll go, or 1/6 times 15. And it'll go all the way up in scale and give me like a fence that's 15 feet tall. So anytime you're just trying to draw a vertical segment, this is the best way to do that. All right. Now we'll set our window here. So I don't know how long it's going to take for that ball to go 300 feet. But like I've been to a baseball game before, and there's not usually instances where a ball's in the air for more than 6 seconds. Right? So that seems like plenty of time to me. You guys agree? Especially something that's hit at like a 16-degree angle. That's pretty much a line drive. I bet it's probably not in the air for much over 2 seconds, but whatever. 6 is fine. The X value, I'm going to go from 0. I know it's got to be more than 300. I'm going to go to 400 just to give it a little bit of extra space there for me to see what's going on. The height is going to go from 0. And if I hit a ball 300 feet at a really shallow angle, that's pretty much like a line drive, right? Using baseball terminology, if you're not familiar with that. I don't know, that's just what they call it, when a ball that's hit pretty straight rather than really high up. So I'm going to guess that maybe 50 feet, that it's hit really far, so it's got to go up a little bit, but it's not going up very much relative to how far it's been hit. Just kind of guessing. If I don't get a good picture, I can always go back and change these things. And I'm going to hit graph. So there's my ball. And there's my fence. And you can see there that definitely that ball didn't clear the fence, right? You guys cool? Okay. So again, that just kind of backs up what we were seeing algebraically, or numerically, I should say. What if we ask a slightly different question? What if instead we ask, like, how far can we place, or like, let's say how far, if there's no fence, how far would that ball travel? Let's say, be specific here, in the air. Right? We're not talking about it rolling on the ground after it lands, right? So what would I do here? When is the ball going to stop being in the air? When its height is 0. So I'm going to set y equals 0 and solve for t, and then plug that t x. Do you guys feel okay there? So let's see, what was my y equation? I just had that a moment ago. So I have 0 equals negative 16 t squared plus 135 sine 16 t plus 3. What kind of an equation is this? Quadratic. To solve this quadratic equation, what am I going to have to use? Got to use the quadratic formula, right? There's no chance in me factoring this thing with the sign in there. Okay, so t equals negative 135 plus or minus the square root of 135 sine 16 squared minus 4 times negative 16 times 3 all over 2 times 10. What would be even better than doing this, though? Do you still have the quadratic formula programmed into your calculator from last year? If you did, that would be, you could just plug in the values for A, B, and C and get your decimal. I don't know that I have it programmed in my calculator computer. I don't. Oh, drat. All right, so negative 135 sine 16 plus square root 135 sine 16 squared minus 4 times negative 16 times 3 over 2 times negative 16. That gives me a negative value, which is probably not what I'm looking for. So let's go ahead and recompute that, but we'll put it as the minus. Right? Instead of negative 135 plus, I'll do subtraction. So 2.4. Right? We always want two answers. The bigger answer is going to be the one that we want because that's going to be the one that's furthest. And then to get my value for x, then, I'm going to go ahead and plug that back into my equation. So I have 135 times cosine 16 times t. So 311.9 feet. Cool with that? One more question we could ask. So what if we asked what is the maximum distance from home plate that we could place a fence, that same 15-foot tall fence, and still have the ball clear the fence? How would we figure that out? What does the height of the ball need to be to clear the fence? 15 feet, right? So we're going to plug 15 in for y and solve for t, and then plug that t into x. Basically, this exact same idea as the previous problem, right? You guys cool with that? Equals negative 16t squared plus 135 sine 16t plus 3 becomes 0 equals negative 16t squared plus 135 sine 16 minus 12. My calculator. I'm going to borrow the work from my previous problem because all I'm changing is instead of the 3, I need to change those 3's to negative 12's, which is a pretty good deal because that's easy to do. Change that 3, because C's only in there one place, right? So there's that answer, but I don't know that that's necessarily going to be the biggest one. So I also want to double check and make sure that I've got the best answer there. Oops. Yep, so about 1.9. So x equals 135t. Or about, oh, stupid on me. Let me get rid of some of this stuff. There we go. Now I can do it. It's like, that's not right, because it's taking the wrong answer. There we go. So about 251.6 feet. What do you guys think? Yeah, that's where I'm at too. Okay, so from 10.1, you guys should be able to do up through .40. From 10.2, you guys should be able to do 41. And 10.3, which you guys are going to do on your own on the asynchronous day. So I think that's Thursday. You should be able to do up to 62. I think. Yeah. Yeah. So it looks like a lot of problems are really not so bad, because a lot of them are just like doing silly things like, you know, graphing the thing on your calculator, filling in a table of values, you know, or like the section 3 is just about graphing things on polar coordinates, which shouldn't be too bad for you guys to do on your own. So it's not, it's, some of these questions should be quite straightforward. Not all of them are super easy, but a lot of them should be pretty okay. So this will be what the homework check on Sunday is looking for. So you have basically the full week to kind of pick away at these things also. You know what I mean? All right, well, we'll stop here.